Yes, cool. Okay, everyone, today I'm going to talk about from words to worlds, bridging linguistic and spatial intelligence. So some context, I was trying to do like a mock talk for my job talk. So there will be some words that from a long time ago, and welcome people to send me like feedback after the talks. Thank you. Yes, cool. So now we're already seeing so many linguistic intelligence models from different companies, right? They're basically trying to fight on the leaderboard, saying like who is the best. And for myself, my life cannot live like without this kind of linguistic AI already. But seeing this AI has already been so excellent, can they actually being able to solve all of our real world tasks? Let's think about like a really bad scenario. Just for example, at this specific moment while I'm giving a talk and the screen behind me here is on fire, right? So what would you do? I have two solutions for you. The first one is that you can ask a chatbot, like relying on it to resolve this problem for you. So what would you do? I would like grab my phone and type fire, fire, fire. And the screen is on fire, immediate help needed. And then the chatbot will think for 2 seconds and then give you the solution. You read it, okay, cool. And now I need to get out, problem solved. So if you choose this solution A, I won't blame you, but it will possibly endanger your life and your personal property. Then let's think about another solution B. If we have an embodied agent who is able to perceive and interact with this space, what will happen? So, okay, the robot itself will, see the fire, and then looking at the environment around, figure out where maybe the fire extinguisher is, figuring out how to use this extinguisher, and then like aim at the fire or me, and then like trying to extinguish the fire. Okay. If there is really an ideal like physical intelligent AI like this, then congrats. Okay, you win this game. Your life and personal property might be safe. So I want to stand on the winning side of the team. So let's see like what are the difference between this chatbots and this kind of spatial physical intelligence AI. So in the first scenario, actually the input and output of this system are text only. And we human ourselves lives inside this 3D physical world, right? We have this perception system to perceive and abstract the situation and send it to the chatbot. And the chatbot only uses its linguistic ability to think and reason about the situation. And then it gives us text instruction. And our human has responsibility to read and physically interpret what happened. But in the other situation, the robot itself has this kind of multi-sensory spatial info sensor and is able to do this kind of physical interaction. So as a human, we don't actually need to process this data and abstract them linguistically. Actually, we don't even need ourselves to present to solve this kind of situation. Let's say, what are the fundamental difference? From my perspective, I see it is the level of spatial physical involvement are different. So what my work is trying to work on is that how we are able to build a real physical interactive intelligence that's moving from this linguistic intelligence that is not only able to reason about the 3D environment we live in, but also like reason within this environment. So yes, so this will have lots of application. I think we'll have some overlap with the audience here. For example, like in virtual design, if this understands like the environment and the environment itself, it can help us do more creative designs. and generating more realistic and physical plausible animation, and will also help us give us better experience in mixed reality. And the better thing is that this ability help us to build better robots in real life. It cannot help us only build more physical intelligent robots that is able to interact with human more safely, but also help us in the way of rehabilitation to further strengthen us as a human. Cool. So before saying how we do the physical part, let's go back here. So we're already seeing there's a lot of linguistic intelligence here. And so what makes them so capable? Okay, so my answer here is that first, we already know, to train them, we have a good training architecture. And also we need good training strategies and also proxy tasks to train this agent. And the last and the most important. Okay. Yes, we need more data. So none of them can spell these magical spells without the massive amount of data it has seen on our internet, right? But the problem is we see the similar trends also in this low-level vision task tool. For example, VGGT, it has better proxy task for training, has a good foundation model, and also it has tens of millions of image to train this kind of low-level foundation low-level vision policy model. Yes. So the question comes very naturally, how about we just scale up the data, right, for this kind of physical, spatial physical rich tasks? Very plausible, but we need to take a look at what kind of data we need. So let's go back to this task again. So first, the agent needs to interact with objects. So it needs to some extent understand how the object works or how the object looks like. And secondly, it needs to interact with this object. So it needs to know how to move and how to use to interact with this object. And the thirdly is the environment itself. It's not only standing alone as a robot, but it's actually within the environment itself. So Into has the ability to do object search or a basic modeling ability of the environment around us. So okay, looking at all of these three, we do need lots of data. So even though for example, for the 3D object community, has already having tens of millions 3D high quality models. And also in an object interaction community, there are lots of people that are trying to collect this scale of the data. And also not only in the simulated environment community, but also in real world scale. We're now trying to reach as large indoor scene environments. The scale of data we're having is becoming larger and larger, but this is far away from us to actually reduplicate this kind of 3D environments and the interaction simulation in a simulator. So what can we do next? There are three solutions we're having. So first, you can have money and time. There's lots of cooperative effort. I'm knowing they're trying to collecting this large scale demonstration, but I don't have that. The second effort we can do is this kind of large scale community effort. I think this is actually, I think lots of people in graphs are actually involving this kind of large scale effort, and this is very doable. Yes. But let's say as ourselves, as a small community, what else can we actually do? Is that, so here what I'm proposing is that can we actually using language as a scaffold for general spatial physical intelligence? So what do I mean here? Okay. So for example, we're a human living in this physical world. we have our perception and action system. And this perception, as we already talked about, is related to like different aspects of this 3D physical world. Similarly, our embodied action. Okay. Okay, it's also like ranging from like whole body control, like also to dexterous local manipulations. So like there's lots of aspects like related to embodied action. Okay, maybe this thing is our problem. Okay. So let me see. Okay, very bad. This is out of power. So can I just like click it here? Yeah. Oh. So yes. So okay. Why this is stuck as well? Very quick. Okay. Yeah, I don't feel like that AI to help me solve this problem. As me, this is my
chatbot.
Yeah, suboptimal solution. So yes, so actually, like in lots of physical perception action loop, like we don't actually explicitly need language. So there are some like the connection directly in perception action. But as we mentioned, if we try to like collect this kind of pairwise the data that enough to train the system end to end is actually very challenging. So therefore, as a human, we have this magnificent language intelligence. So given this, what we can do is that using it as a hub to like train different submodules that's link action, perception, and link action and language and perception language, and using language itself as a hub to solve this perception and action task. And even better thing is that if you have robot system, even though it has different perception and embodied action system because of the difference of the hardware deployment itself, you can still use language to communicate with robot because language itself is actually a universal interface for this kind of like communication. Okay, cool. So some people may argue that saying language is too selective, abstract, and does not fully capture the richness of perception action, which I partly agree. But if we like look at some like literature in cognitive science, there is a phrase I really like from the famous Steve Pink's The Star of Star. So when it's talk about when he argues about the concept of time, he's basically saying even though time itself are continuous, but human actually experience in an event-based discrete manner. So I still think there are people perceive and make sense of the concept only when it matters to the people. So language itself actually reflects the human thought of space, and using them as a natural hub, it will not only be very intuitive, but also have the potential to generalize to the broader case. Okay. So now let's talk about how my research can start to like develop, delve into this sub problems of this spatial physical intelligence. So my research is actually not only focused on one problem, but a general spectrum of the whole spatial physical intelligence task, including dexterous manipulation in embodied action, and large-scale scene generation and understanding. And lastly, we look to a very detailed of like geometry generation problem. And so, okay, So first, let's get started to look into this dexterous motions problem, and let's see like how we're able to using action-centric verb to create a very generalized data set that is able to generate like diverse like hand manipulation, hand action generation problem. So yes, here we start to present like this work called GigaHands. This is work that we published last year in CAPR 2025 from my co-workers from Brown and ETH. So what we know is that we as a human using our hands very dexterously, like I almost all the seconds our hand is actually interact with ourselves, with the environment, or with others. And this is a part that's most frequently for us to physically interact with the environment around us. But in terms of data collection, there is like a major problem that is commonly seen diversity and accuracy trade-off. So one way that people use to collect the data is that using this kind of easily carried sensors, like for example, our phones, our cameras, or these wearable glasses. So for this kind of modality, like we're able to, for this kind of sensors, we are able to create a large scale of data set that is in real life, which ensures the diverse action. But the problem is that this data usually like we're by human, and when we're doing tasks, we're not actively staring at our hands. And also because the deployment of the sensor itself, making the 3D tracking very inaccurate. But us as a lab, we have another kind of solution that is the reverse solution of this. Instead of bringing sensor to real life, we bring human to a very sensor-rich environment, like in this studio setting. So with this sensor-rich environment, we're able to track very accurate 3D. But the problem is that we need to spend a bunch of money and time to create like as much stereo as possible. And it's very hard for us as a lab itself, like to collect the thousands of hours data as we did in the wild setting. So in our works here, we propose this work called GigaHands. So what we do is that we use this verb-centric action sourcing method to try to source motion and replicate the motion in real life setting. And on the other hand, we're still capturing all the data in a markerless motion capture system so that to ensure the 3D accuracy and the quality of the data. So before we talk about how we actually source and create diverse data sets, let's take a look at the motion capture setup itself. Okay. The capture setup itself actually is built at Brown University, and this setup itself has like 51 synchronized RGB camera. So when a person is trying to collect the data, they can either stand or sit in front of the capture system, as long as they put both their hand inside the system to making sure like the bimanual activity are captured. And with this setup and 51 cameras, you can track hand motion very accurately. And at the same time, you can track the motion of large-scale objects very accurately. Okay. What else you can do is that you can also like dynamically reconstruct the whole thing because we have this 51 camera setup. And also the physical tracking itself is accurate enough for us to do this physical tracker into robot gripper in a simulator setup. So this is an example of uni-manual lifting, and this is another example of bimanual manipulation. Cool. So now we talk about the capturing setup. Let's take a look at how we generalize, we capture this large-scale generalized data set. So our intuition is actually very easy. Okay. I think the more number of verbs in your instruction script, the more diverse your data would be. And to like trying to see if this assumption is real, so we design this procedural instruction generation method. So what we do is that we first find like the source that there could possibly this data could possibly contain the annotation of possible human hand motions. And then we use a very simple semantic parser to parse out all the actions. And then like for myself, this part is semi-auto. I need to take a look at all the verbs, so my repertoire like grows quickly during this project, and see like what are the meanings of these verbs, and find those objects that could prompt these verbs out. For example, like let's say the verb beat. When it's related to the object egg, you may refer to the stirring motion that beating an egg. But if you're saying I'm beating someone or something, you might do a very violent behavior, like punching. So here what we do is that we find the objects that could prompt this motion out, and we categorize them into scenarios, like given the occurrence of this object could occur in different kinds of scenarios, like cooking, crafting, officing, entertainment, and office work. And after that, we feed each scenario into ChatGPT. We ask ChatGPT, like, given all of these verbs and all of these objects, what could be the potential like seeds that is able to prompt all of this verb and the object pairs out? And it gives us some like possible solutions, and also like the combination of possible actions and the verbs that you use in the scenario. Cool. And lastly, what we need to do is that we further ask ChatGPT to expand each verb out into an instruction, and then asking it to add instruction in between instruction, or like modify the instruction slightly to making sure that this is actually instruction that can be filmed sequentially without lots of moving of the objects inside and outside of the system. And finally, I still like eyeballing checking like all of the instructions, but there's not too much of them. It's only like 1,370 of this instruction. Okay, now we show that how we turn these 500 verbs using a procedural generation method to expand them into detailed instruction. And each of them is like an atomic level action. What we need to do next is very simple. Like we basically turn each instruction using a like text-to-speech like software, turning them to video and play them to participants. Participants listen to the instruction and act accordingly. And because like all the instruction, all the film video itself has already paired with the instruction, so we do not need to do further text annotation next, like those web source data set do. So all the video itself is already paired with a meaningful text annotation. What we need to do is just further to modify this video in case that there's some like unnatural motion or like some motion that are unintentionally acted out during this filming process. And eventually we have 14,000 of these motion clips, and then we further augment the text and pair all these motion clips with 6 text annotation, 6 text description. So eventually we have this 84,000 of text description that's matched with the motion clips. Okay, so eventually, like we have this diverse set of data we collected. Okay, and speaking of the number, it is like so far the largest scale of data set that has the 3D hand and the text annotation pairs. In total, it has 34 hours of demonstrations, and as you mentioned, it has 14,000 demonstrations. And every second of this data are actually semantically meaningful. And yes, if you look at the verb diversity, we'll notice that we do this kind of comparison with equal x or 40 and equal 40, and we saw that in our data set, we actually have like 1,400-ish words that is comparable with the number of verb equal 40. And thanks for ChatGPT's augmentation, we actually have 580 verbs that uniquely belongs to our data set. But really, that's more verbs means more diverse motion. So we have these questions. So we actually do a visualization for this data. And what we do is that we compare the 3D, all of the data set that has this kind of 3D hand motion annotation. And we do like a t-SNE to actually visualize the distribution of the hand pose and the hand motion of all of this data set. And the blue dots means like this pose or this motion is from our data set. And we do notice that is the wider coverage of pose and motion from our data set. And if you look at the boundary of this like this convex shape, if you look into some dots that as the boundary of this convex and look at its corresponding text description, you will realize that this text description actually are uniquely belongs to our data set. For example, this like noting or dotting or like motion of measuring. So this text actually uniquely belongs to our data set. So we will say this unique verb itself actually contributes to the diversity of the data set itself. Yes, and then we see how the model works in this kind of generative task. So what we do is that we input a text, we train a text to motion generation model, and we put the text description of like what we want, like for example, fastening the V. And then the generative model is able to generate like very realistic, or the motion itself actually makes sense and correspond to the text instruction.
How do you evaluate?
I'm sorry?
How do you do the evaluation?
Evaluation,
yeah,
we just do the traditional like FID, and also to see like how the generated motion looks like the ground truth motion in the data set, and do this like multimodality distancing, that is to train compressed latent space with motion and text matching and to match their distance. Does that make sense? Yeah. Yes. And yes, and also like I expect some of the example, and they're very interesting because if you see compare the generated results and the results that retrieve the most similar in the training set, you will actually realize the generated motion itself is not only smoother, of course, because the large scale model help you, the differentiable operator help you to smooth this motion out. But it actually help you to avoid the excessive motion, making the motion more aligned with the text itself. What I'm saying is that if you look at the example on the left, the text prompt is like fastening the lid. So the generated motion actually grab the lid and fastening it. But the data which retrieved from the training set, it actually grasp the lid and the switch hand, and then fastening it. So the model itself somehow like realized this switch hand does not align. Yes.
Yeah, I want to ask a question. So is objects part of what is in the system?
Yes, the object tracking is in the system, in the data set itself. But when we are training this model, we did not use objects, any form of object input. So it's only generating hand motion. And we just see if this hand motion like makes sense.
From text.
Yes.
I see it. But how would you know it actually fulfill the task?
We can't know because as we mentioned before, when we are measuring it, we only measure the motion like in a latent space, whether this motion like is semantically close to the text description. Yes, so it's more like a perceptual, linguistic perceptual study, not actually put them in a simulator. Yeah.
Do you do any like user study, like a game where the user has to guess from the hand motion, like what the text description is and see the alignment that way?
Yes, that's very interesting thing. But we didn't do that because we thought this could be measured like quantitatively in the way we mentioned about. Yeah. Yeah, thank you for the question. Yeah, let's moving on a little bit. Okay, and we also do this test of the like plotting this scaling law curve, like by doing this text motion synthesis of a different partial of the data. And as you see, like the more data we're having, the better the quality of the generation and the better of the semantic alignment. But even though we have 34 hours of data, the curve itself looks like way like far away from actually convergence. So yes, we should actually collect more data. So to even like making the current like text motion generation model to converge.
What is reconstruction?
Reconstruction means like you just compare this with ground truth. So this one is to like say measure the FID of the generated data and the test set validation. So this one is just like I just guess the test set ground truth validation data itself and calculate the FID.
Okay.
With the ground truth.
That's the perfect case.
Yes, that's the like upper bound.
Oh.
Or lower bound.
Lower bound.
Yes, of this scenario. Yeah. Yes. Okay, so another generalization thing we can do.
Yeah, question, if you can go back,
Yes.
why does the ground truth lower bound get slower as the data increases?
Okay, this is a great question. I think it's the more data you are having, the latent space you are constructing, maybe this is my assumption. The manifold itself is more smoother and more making sense. So like when you're calculating the FID using the feature from latent space, maybe it looks just better.
Or because
Yeah.
this latent space is trained on the ground truth data
Yes.
and it's not constant. For every point,
Mhm.
you retrain a different latent space
Yes.
and you use that to evaluate the generation.
Yes.
Uh-huh.
Thank you. Okay. So what else you can do is that you train a motion to text, motion capturing model, and you input like the hand motion. And here the video is just for like a reference to see what the hand motion correspond to. And we are able to generating text annotation accordingly. But one thing we want to highlight is that even though you only train this text motion model on our data specifically, it's able to actually capture the hand motion from the other data set. Another thing I want to say is that even though it does not see any objects in the hand motion itself, but it's able to guess what's inside this thing. And this kind of guessing is actually like kind of making sense.
So you're using so it is still predicting from text.
It's like your input is hand motion itself, and then the output is text.
Oh.
So the text is guessing, looking at the hand motion, guessing like what object you're interacting with. Yeah.
Oh,
How is this possible at work? Sorry, like,
Mm.
by looking at you at the two hands, I would have never guessed that there is cream and teacup.
Yeah, that's a good point. So actually, maybe these are not the cream or the teacup, and this motion itself is not slicing apple, but it's like, for example, in the ground truth video, there's nothing there, right? But itself, like you see the data pattern like this, in our data set, like it's slicing apple, so it just generated something saying like I'm slicing apple. Yeah. So I would say maybe like there's still no meme, like there's people like performing without object, but audience still able to guess like what are those action is. So it's something similar to that.
It's just that evaluation now is even harder.
Yes. Mm. Yeah.
Right.
Yes, I think we need to like move forward a little bit. Yes, so in this task, we're seeing that actually actions themselves are grounded in verbs. And if you use language or this verbs as like an anchor to anchor what are the possible motions, we're trying to collect or we can try to make the machine to replicate, we're actually able to collect this data set very efficient, generalized, and high quality. And the similar thing actually also applies to some like tactile data. So one of our current work is trying to like prompt all those vocabularies about like material and the velocity, motion, and change of state to collect a large scale data of hand object interaction with tactile data. So please wait for another few months. Yeah. So we talk about how like we can use verbs.
Sorry, before you move on, can you tell us a little more about the hardware setup? So you said 51 cameras.
Yes.
Do they all detect the full hand? So like you run hammer on all of them. How do you merge the different predictions? Is it averaging or some of the form optimization?
You mean for the hand pose optimization?
Yeah, for the hand, for the objects, like.
Yes. So in general, this is actually a similar setup here, right? Except we have this glove. So we have this 51 camera views. And when we're doing hand motion tracking, what we do is that we estimate the key point of hands across all the views. Then we do triangulations. Then we do inverse kinematics to guess the accurate 3D hand tracking. And then for the object, what we do is that we scan the object with my iPhone, and then like we use like grounding STEM to get the mask of the objects across the whole video, and then we use the virtual renderer to track this object and get this 6 dot.
We detect the key points.
Yes, we maybe can chat about the detail later.
Okay.
Yes, cool. Yes, so yes, so like, but look at like the environment around us, right? There's not only action, it's not only me like waving my arm. That's the only like spatial concept there. There's also like more complex concept that lies in this. There's more complex concepts like spatial relationships that's inside this environment. Yeah. So now let's take a look at like some of my works with this, that how we are able to using like different spatial functions or some like action functions that's able to generate large scale or understand this kind of large scale scene. So this is one of my work we did. It's called like AnyHome, open vocabulary generation structured and textured 3D home. So in the setting of AnyHome, what we do here is that we input a text description, and the model is able to, according to the text description, generating the complex layout as well as the texture inside the room. And how we are able to generate this complex structure environment. So we have a very like simple observation again. So actually, there's lots of study, not only this one, that in cognitive science and linguistic study, like in English, there's only like 80 to 100 spatial prepositions in English that describe the relationship of like this objects and spatial structures. So what we do is that for like indoor environment, we extract this possible spatial prepositions and convert them into a differentiable function. For example, this line has like place tall. That's the simplest. So we just turn this place tall operator into a like a differentiable function that's saying like the max of B is smaller than the mean of A. That's mean that B is under A is on top of B. Okay. And with this differentiable spatial function constructed, what we can do is that we can actually structure them together like into a graphic structure. For example, if we want to represent a house floor plan, we can represent each room here as a block, and the line connected here is a like predefined spatial function we're having. And similarly for like indoor room layouts, what we can do is that for each node here, we represent like object, and the line here represents a predefined spatial function. And in this way, we can get a very complex indoor layout. And similarly, like we can turn them into an actual 3D geometry by retrieving the objects in a large scale data set. Now, with this method, we already have structured geometry. But then the question is that how we're able to convert the user inputs to this kind of constrained graph that have this kind of spatial relationship, right? So we realized actually LLM is a very good tool that is able to transfer like human linguistic description to this kind of predefined constraint graph. So here we use a LLM and designing its prompts and do some like prompt tuning, trying to making sure that given a text input is able to converge into the predefined constraint graphs. Then we have this complex geometry, but it still does not have the details like the good object placement and the texture we mentioned about, right? So what we can do? So actually for human, for a complex indoor environment, there are two sets of perception systems. One here, we call it allocentric perception, that is see the environment as a map. Thinking about if you want to buy this house, the house agent might give you a floor plan of this map like this. So you are seeing the holistic layout of this environment. And another perception system is an egocentric system. That is like how we human as first perspective look into this environment. So that's in egocentric system is more like, okay, now I go inside the house and inspect how the house looks like. And in this way, you can inspect many details of the environment in egocentric. So what we do next is that we convert this generated structured geometry, like using some algorithms in size distance view, and converts this geometry into an egocentric trajectory that's mimic that human navigate inside the house. So with this trajectory, you will see some geometry that looks like this. Okay. Now, with this egocentric perspective, what you can do is that you can see what objects are placed incorrectly, and then using algorithms to fix it. For example, the bunny was like floats on the top of the shell. You can use VLM or using differentiable renderer to actually place the object exactly on the top of the shell. And you can also add texture to this environment using depth conditioned imaging painting. So you can see as you're touring inside the environment, the texture itself like grows out from the environment. Yeah. So with the 13 predefined rules we mentioned before, you're able to actually generating a very complex like spatial structure. And you can even scale it up to a house scale, as we see here. Okay, I'll go through this really quick. Yes, so in this set of work, we see that human actually use just a very limited set of predefined prepositions, and language models are very excel using them. So this concept actually help us to use this preposition words as a scaffolds to build out very complex, like large-scale spatial environment. Yes.
Can you show us what is the pipeline for the generating this 3D?
You're generating the structure or the environment?
Yeah, given a language command. How is it generated?
Okay. So let's see. Okay. So in general, like give a language command, we'll have prompts first to like disassemble this task into first floor plan generation, like room layout generation, and small object placement. And we will give them like a set of rules as we saw here. Like ask it to specifically using like the rules we described here. And this is only the example for room layouts. For floor plan, we have another set of rules. So we do this hierarchically. So we first input the text prompt from the users, and we ask it to use the rules to select the rules for floor plan, ask it to generate the floor plan first. And then for each room inside, we will again, like given the like the user's input, and ask it to generate to select the furnitures for this specific room first, and then use rule to connect this furniture using like ask it to select the rules or to place this set of furnitures inside of this environment. And then it will generate a graph like this. Yes. And finally, like we'll ask it more, given the context, we'll ask more detail of like how the style of the furniture may looks like, and then using this text description to retrieve the specific furniture in the base. Yeah.
So additional input is the list of the furniture
That
in addition to the language command, or all
Yes.
the furniture. in
Yes.
the language command?
So you need a data set of furniture itself. Yeah, so the input is still user input, but in the output, the first step is the floor plan, the second step is the layout, the last step it tells you like how the furniture should look like. Yeah, and we use like text image based similarity to see like inside the data set like which furniture we should choose. Yeah. Thank you. Okay. So, yes, so I just mentioned this work really quick. So yes, we can actually using this simple rules to create data set that is able to perform on this very complex spatial perception task. And with this work with my colleagues at Meta is called SingLM. So what we want to do in SingLM is that we want to make an LLM able to understand 3D. Okay. So with the input to the LLM is like the 3D representation of this thing, and a question about the thing. And the output of a SingLM is like the answer to the thing, and it is able to answer a very diverse set of questions. So what we do here is that first we have this 3D data of this environment. in egocentric view. And we use an image captioning method to caption this egocentric representation of this 3D scene. All we do next is that we feed this 3D feature of this environment and pair them with the egocentric caption of this environment to align this 3D features to the language feature embedding space. Okay. The second step we're doing is that so for each 3D scene, there's lots of properties that we care about. Not only for the like spatial relationship we mentioned, but also about like what are the members of the objects and what are the entities existed in this specific data set. And we ask LLM to convert this kind of properties that we care about into this question answer pairs. And then with this paired data, what we do next is that we still input the 3D feature of the scene, and we input the question that the LLM generates, and also the answer that the LLM generates to train it as like a QA module of scene text module. And yes, so even though this data only trained, so even though this model only trained on the data like we prepared before for the like the spatial properties we think that's like in 3D reasoning people care about, but it's able to actually by 2024 these other methods on holdout dataset testing, like in this kind of QA task setting. And of course, if you fine tune it, it performs better. And another thing it can do is that you can further fine tune it with like a predefined set of motion that the egocentric agent is able to do. So with that, it's able not only able to answer like a natural language question, it is also able to tell you, okay, for the next step, for this specific agent, what are the actions you can use from your low-level controller? Yes. So this work actually shows that actually you only need to like create this data of the properties that people like care about, and you are able to like having this model performs very well in held out 3D QA data set. So it seems like at least so far the current data sets, there's still like very limited concept that people are actually caring about. Okay, so given the space of time, given the short limits of time, I will just give this part really quick. I will just talk about this part really quick because I think my advisor actually presented this work 3 years ago. It's like how we are able to generate fine granularity geometry. That is very hard to be described by language accuracy. So the high-level idea we are having is that human actually describe a 3D shape or object around us like recursively. The language itself has recursiveness. By saying that, I mean that when people trying to describe an object, they tend to like iteratively add attributes that describe the specific object. For example, people may say like, this is a chair, and then you want to describe more fine granularity property of this object. It will say it has separate legs, and then it says the armrest can hold, and then it says it has wheels on the chairs, right? So what we do is that instead of giving all of the text input, text description to the module, we actually use semantic parsing to parse them to small attributes and feed the model gradually so that the model is able to like grow in the chair from the raw initial state to this very final state, which contains all of these semantic attributes. And this example is the one I really like because it actually has bones at the bottom of the chair, which is very rarely seen in the original data set itself. So it shows that our model is using the recursive nature of language. Our model is able to generalize object slightly out of the distribution of the training. Okay, so I will skip about the technical detail and some visualization. So, yes. So lastly, we have already seen like how we're able to use verb-centric, action-centric verbs to help us like collecting this large-scale data, and how we're able to using predefined spatial prepositions to understand our scene better, and how we are able to using the recursiveness and symmetric attributes of the text description itself to understand how like fine granularity geometry, like the presence of fine granularity object geometry. So in general, my work shows that by using these styles of space, it's very useful as a semantic anchor for data acquisition. It is also can be used as a scaffold for like this large-scale structured scene composition. And lastly, the source of space itself actually also mirror how human perceives the environment around us. And lastly, the thought itself is a powerful human-machine like interaction surface, and it's enabling the interaction that's interpretable, controllable, and more safer. So for some future work I want to mention is that. So let's look back at the original task set we are having. So we study about like how text can help us to understand the object itself better, how to understand how to manipulate the object better, and how to understand the whole environment better. But what we actually want is a more end-to-end system that is able to solve this long context, long horizon, the whole body task. So I think there's still like systematic work that we need to do to actually make the 3D assets we created actually more end-to-end and also more simulatable. And we need to figure out how the language interface should be placed in this like long context, long horizon, whole body task. Okay, another setting is that still there's lots of properties that are not linguistically describable, and how we should able to provide better interface for the high-level planners. For example, in this in-hand dexterous manipulation task we present. So one assumption is that I think there's many interesting work that's studying the phase modeling of human action. So maybe we can collect a lot of complex manipulation tasks in this phase manifold. Okay. The last thing is that I noticed lots of people in this lab interested in manifolds. Sorry. Okay. In deformable objects, so I just made this demo. So like for very complex deformable objects, for example, this one, a person lifting a mug, the dynamic of the object itself is very hard to be described by language. So how we are able to capture this model better, capture the deformability and also modalism better is also a direction I'm studying. So lastly, thanks for all of my collaborators, and thank you for the amazing questions and having me to present here. Are there any more questions?
Very interesting. The question about going from allocentric to megocentric to allocentric was very intriguing, because the commands are usually not given in a design, they're given in a real egocentric, the way where the left and the right are differently defined than when you are looking from above.
Yes.
So you're still you're creating something in a coordinate system. So the final coordinate system is a allocentric system, like it is in the room, like you see vertical, like X and Y, like this, or so when you create these point clouds or meshes there, what is the coordinate system?
Yes, so they are not equivariant representations. So actually, like in the scene, like we just going to assume Y as up, And similarly for object, we also assume like Y as up. So they're all in a canonicalized space. But in the scene generation thing we're working on, we actually perceive it as a metric space. Yeah. The scale itself is metric, but it's still like the coordinate system is also like this is Y is up.
But at which stage does the system map the left, right, the way it is from my point of view? Like a lot of propositions are egocentric, right?
Yeah.
And from most of them.
Yes.
So how does the system know how to map these propositions from egocentric to the canonical?
Yeah, that's a very good point. So for the generation task, because we already have the predefined structure itself, and we have this trajectory generation algorithm, so we know exactly where our viewpoint is at. So we're able to just like convert like this left and right very natural.
Oh, I see. You just apply a transformation.
Yes, but
Okay.
for the scene like perception task, actually like if you look into the data set, we have both egocentric and allocentric systems. So we just treat the first like view frame like as 0, 0, 0 and assume all of them are like Y up. And then we use a metric scale for like this kind of task. Yes,
Okay, very good.
thank you.
Following up, you have a part that try to make it physically grounded, like for example, it touches the ground. Why do you need egocentric views to do that?
Oh, that's because the data set itself, like not lots of data are like canonicalized very well. So even though like some are like saying like the metadata is given are incorrect, you can think about that. If we directly retrieve it using the metadata in the data, that could be wrong. So we need to like actually look at the geometry and fix them.
Yeah, you do the geometry, but you can do the physical simulation of anything. You don't need to be in the person to do the physical simulation.
Yes, that's correct. Then you need to put it into a physical simulator. But if you're the surface, like the bottom is not really evenly flat, the thing may fall off. So for animation purpose or visual perception realistic purpose, this is like how we choose to solve the problem.
Oh, because you not only use the physical simulator, you actually use some image learning based.
Yes, like perceptual based.
Perception method to basically reduce the gap, remove the gap, for example, between the object and the ground.
Yes.
And that can be seen from the first person view.
Yes.
So you deal with that in that image space.
Yes, that's correct.
That's it. Thank you.
Thank you. Thank you. Thank you.
We could talk. Yeah, very good. You're good.
Yeah, thanks for the questions and
Of course.
yeah.
Yeah, I would put them on a bit more detail of architectural work.
Yeah, I think there should be a part that can go more into the depths and stuff. Yeah.
That's
Yeah, thank
very
you.
good work.
Yes.
Okay.
Oh, big ones here. Wait. Yeah. I think next year meeting with Linguistic. Oh.
We have a meeting later.
We have.
No, we don't. I actually don't have I don't get the email. If I got the email, I will.
Yeah.
I haven't grabbed, but maybe it's like first is for
Oh,
very
okay.
student, then postdoc, so probably it's filled out. I'm not sure why.
Oh, yeah, sorry about that.
And the like the grasp general, or actually no, like some of the PhDs.
Yeah.
Oh, and you're a
I'm
postdoc.
postdoc. Yeah.
Oh, I'm so sorry.
No.
Yeah, we usually send it to the full grasp now, but the itinerary was full before we had a chance to.
Yeah, I guess that's okay. So yeah, no problem.
Yes, but we can chat later
Yeah,
anyway.
we can chat later.
Yes.
Yeah, but what's your Actually, Leon knows the schedule. Actually, I can find the schedule.
Okay, but because my flight is tonight, so
Yeah.
after schedule, I need to go.
Go immediately.
to
We can talk later then.
Yes.
Yeah, no worries. Okay,
Yes.
okay, yeah. Great talk.
Thanks for the questions.
Sure, see you around.